Graphs of linear functions. When we are working with a new function, it is useful to know as much as we can about the function, its graph, where the function is 0, and any other special behaviors of the function. We will begin this exploration of linear functions with a look at graphs. When graphing a linear function, there are three basic ways to graph it. 1, by plotting points, at least 2, and drawing a line through the points. 2, using the initial value, output when x equals 0, and rate of change, slope. 3, using transformations of the identity function, f of x equals x. Example 1. Graph f of x equals 5 minus 2/3 x by plotting points. In general, we evaluate the function at 2 or more inputs to find at least 2 points on the graph. Usually, it is best to pick input values that will work nicely in the equation. In this equation, multiples of 3 will work nicely due to the 2/3 in the equation, and of course, using x equals 0 to get the vertical intercept. Evaluating f of x at x equals 0, 3, and 6, f of 0 equals 5 minus 2/3 times 0 equals 5, f of 3 equals 5 minus 2/3 times 3 equals 3. F of 6 equals 5 minus 2/3 times 6 equals 1. These evaluations tell us that the points 0, 5, 3, 3, and 6, 1 lie on the graph of the line. Plotting these points and drawing a line through them gives us the graph. When using the initial value and the rate of change to graph, we need to consider the graphical interpretation of these values. Remember, the initial value of the function is the output when the input is 0. So in the equation, f of x equals b plus mx, the graph includes the point 0b. On the graph, this is the vertical intercept, the point where the graph crosses the vertical axis. For the rate of change, it is helpful to recall that we calculated this value as m equals change of output divided by change of input. From a graph of a line, this tells us that if we divide the vertical difference or rise of the function outputs by the horizontal difference or run of the inputs, we will obtain the rate of change, also called the slope of the line. M equals change of output divided by change of input equals rise divided by run. Notice that this ratio is the same regardless of which 2 points we use. Graphical interpretation of a linear equation. Graphically, in the equation f of x equals b plus mx, b is the vertical intercept of the graph and tells us we can start our graph at 0b. M is the slope of the line and tells us how far to rise and run to get to the next point. Once we have at least 2 points, we can extend the graph of the line to the left and right. Example 2. Graph f of x equals 5 minus 2/3 x using the vertical intercept and slope. The vertical intercept of the function is 0, 5, giving us a point on the graph of the line. The slope is negative 2/3. This tells us that for every 3 units the graph runs in the horizontal, the vertical rise decreases by 2 units. In graphing, we can use this by first plotting our vertical intercept on the graph, then using the slope to find a second point. From the initial value, 0, 5, the slope tells us that if we move to the right 3, we will move down 2, moving us to the point 3, 3. We can continue this again to find a third point at 6, 1. Finally, extend the line to the left and right containing these points. Try it now. Consider that the slope, negative 2/3, can be written as 2 divided by negative 3. Using 2 divided by negative 3, find another point on the graph that has a negative x value. Another option for graphing is to use transformations of the identity function f of x equals x. In the equation f of x equals mx, the m is acting as the vertical stretch of the identity function. When m is negative, there is also a vertical reflection of the graph. Using vertical stretches or compressions along with vertical shifts is another way to look at identifying different types of linear functions. Although this may not be the easiest way for you to graph this type of function, make sure you practice each method. Example 3. Graph f of x equals negative 3 plus half x using transformations. The equation is the graph of the identity function vertically compressed by half and vertically shifted down 3. Notice how this nicely compares to the other method where the vertical intercept is found at 0, negative 3, and to get to another point, we rise, go up vertically by 1 unit, and run, go horizontally by 2 units to get to the next point, 2, negative 2, and the next one, 4, negative 1. In these 3 points, 0, negative 3, 2, negative 2, and 4, negative 1, the output values change by plus 1, and the x values change by plus 2, corresponding with the slope m equals half. Example 4. Match each equation with one of the lines in the graph below. F of x equals 2x plus 3, g of x equals 2x minus 3, h of x equals negative 2x plus 3, j of x equals half x plus 3. Only one graph has a vertical intercept of 3, so we can immediately match that graph with g of x. For the 3 graphs with a vertical intercept at 3, only one has a negative slope, so we can match that line with h of x. Of the other 2, the steeper line would have a larger slope, so we can match that graph with the equation f of x and the flatter line with the equation j of x. In addition to understanding the basic behavior of a linear function, increasing or decreasing, recognizing the slope and vertical intercept, it is often helpful to know the horizontal intercept of the function, where it crosses the horizontal axis. Finding horizontal intercepts. The horizontal intercept of the function is where the graph crosses the horizontal axis. If a function has a horizontal intercept, you can always find it by solving f of x equals 0. Example 5. Find the horizontal intercept of f of x equals negative 3 plus half x. Setting the function equal to 0 to find what input will put us on the horizontal axis, 0 equals negative 3 plus half x, 3 equals half x equals 6. The graph crosses the horizontal axis at 6, 0. There are 2 special cases of lines, a horizontal line and a vertical line. In a horizontal line, like the one graphed to the right, notice that between any 2 points, the change in the outputs is 0. In the slope equation, the numerator will be 0, resulting in a slope of 0. Using a slope of 0 in the f of x equals b plus mx, the equation simplifies to f of x equals b. Notice a horizontal line has a vertical intercept, but no horizontal intercept unless it's the line f of x equals 0. In the case of a vertical line, notice that between any 2 points, the change in the inputs is 0. In the slope equation, the denominator will be 0, and you may recall that we could not divide by the 0. The slope of a vertical line is undefined. You might also notice that a vertical line is not a function. To write the equation of a vertical line, we simply write input equals value like x equals b. Notice, a vertical line has a horizontal intercept but no vertical intercept unless it's the line x equals 0.